Okay, these are the notes from 8.3 day 1. Excuse me. We're going to start talking about how polar relates to the complex number system. It turns out when you look at complex numbers, in their polar form, this can actually help us do some kinds of problems that are actually quite a bit more difficult if they weren't in their polar form. And today, just kind of getting the basic connections down. Tomorrow we'll do a little bit more, take a little further with where it's really useful. But today we'll talk about how it's connected, do some converting, do some kind of basic graphing. And I have to remind you guys too of how complex numbers work, so we're going to flash back to that because it's been a while. So let's just start with the basic ideas of complex numbers. So a complex plane or a complex number, right, a plus bi, that's actually rectangular. The a and the b really act like an x and a y, and if you guys remember plotting complex numbers, if I gave you like 2 plus 3i and asked you to plot it, 2 plus 3i, for example, let's say this is 2 plus 3i. From a coordinate perspective, it's just like doing that. So you go over 2 up 3 and you plot a point. Well, that's rectangular, so its polar version, again, will be helpful for us for doing certain kinds of problems as we go through the rest of chapter 8. Some terminology kind of links some things up. So we're going to start talking about find the distance from the origin out to your complex number as the absolute value of z. A complex number in this chapter also is given a name. You call it z. So if you're referring to z, you're talking about a complex number. The absolute value of z is like saying what's its distance. That idea is not, a whole lot different than saying what's the radius if I know x and y. So there's some ideas already connected up a little bit from earlier in the chapter. Then the word for the absolute value of z is called the modulus. So if you're asked to find the modulus of z, that's also the square root of a squared plus b squared. Now that should be familiar, right? There's your Pythagorean theorem coming up again. So think about how many times you have seen that, and here it is, that same sketch again, but using absolute value of z instead of my r and a and b, because we're talking about a complex number. So if you're asked to find the absolute value of z, what you're really being asked to find is what's the distance to get out there. Or the word modulus will also be used. Okay, let's just start with that. We'll start with the basic idea and get you going. A little quick review for complex numbers. So remember how you plot. A 4 minus 2i is basically like saying 4 minus 2 as a coordinate. The modulus is a calculation like doing the r calculation from 8.1 that you should just be able to do in your head. Square root of a squared plus b squared. So if you take a squared and b squared, square root, what do you get? A squared 16, b squared 4, 16 plus 4 is 20, square root of that is 2 root 5. Now what you just figured out as 2 root 5 is that. That's called the absolute value of z, or the modulus. The other two, if you think about them, actually really don't require any calculation, and they're probably just pretty easy to graph. Remember, these are like missing each part of the complex number, so this would be a 0 plus 5i, this would be negative 3 plus 0. A 0 plus 5i would put us right here, and negative 3, 0, right there. If I ask you what their modulus is, there's no reason to use a formula because it's countable. I mean, just look at it, right? 5i is 5 from the origin, negative 3 is 3 from the origin. So those things don't really require you to do any calculation, just sort of think about it for a second and use some common sense. So there's a quick review of complex numbers. Now, we're going to do some graphs up next that involve complex numbers. Oh, sorry, a little bit more with some points. So 2 plus 2i, a little practice there, 2 plus 2i, double it, half it, graph those points, and the conjugate. Okay, so just a quick flashback to talking about graphing complex numbers as coordinates. Okay, now to the other kinds of graphs. The other kinds of graphs we're going to do is instead of a single coordinate, we're going to do a set of complex numbers. And when you do a set of complex numbers, what you're actually going to get is a graph that's created by an infinite number of points that are plotted the way it's described up there in the brackets, the braces. What this really says in kind of plain English is z is a set of complex numbers. On the other side of your bar, in red is a description that behave like or that do what this says. So if you had a set of complex numbers where all the a's were positive and all the b's were negative, you'd be talking about points that are basically describing quadrant 4. So positive a's, negative b's. Well, start plotting those. Well, you do all a set, which means like all the numbers that are like that, and all of a sudden you're talking about that. It would be an infinite number of points, and it would be solid. Actually, it wouldn't be squared off in the corners. I just did that because I'm out of space. But there's a set of complex numbers where all the a's are positive, all the b's are negative. There are certain kinds of styles of graphs. You have an A-B relationship, and you've got modulus. So we'll kind of talk about that a little bit later as we get through the problems. Okay, let's look at another one. Absolute value of z is 4. Now that's like saying a set of complex numbers, which the z can represent that by itself, that behave like, that do what this says. Well, what it says is all complex numbers whose modulus or distance from the origin is 4. Well, if you think about it, if you plot an infinite number of points that are all 4 from the origin, you just created a circle. Because the idea would be 4, 4, 4, 4, those are all complex numbers with radius 4. Okay, so these kinds of graphs kind of sort of have themes going on. They're usually circular, attached to having the absolute value of z, or they're an area, A and B separate statements, or they're something else, which I'll show you in a second. Okay, another modulus problem. So absolute value of z, all the complex numbers, or a set of complex numbers that behave like this or do what this says, where your radius or your distance from the origin to the complex number is less than 3. Well, first of all, you'd have a set of points, but they wouldn't be all the way out to 3. You'd have a dashed line. So really, points that are not quite there, but all the stuff that's less than 3. Well, if you start putting a bunch of points out there, where the radius is less than 3, all of a sudden you're talking, greater than 3, which actually is now sitting out here. But if you do a bunch of points like that, well, eventually what you're going to get is a shaded in area. So all the points that had a radius or a modulus bigger than 3. So absolute value graphs that are like this, or modulus graphs, they are going to be circular of some kind. So the earlier one, the first one, was A and B as separate statements, and that kind of puts you in an area, it puts you in a quadrant. But as soon as you put A and B together, that actually is not necessarily an area. And so what I always do with problems like this is I think about it as, what if it was an X and a Y? Turn it into an mx plus b, and if you can do that, just translate it that way, well then it's going to be simple. Now you're talking about a linear inequality. So a y-intercept at 1 and a slope of -1, but dash because the inequality symbol, and then think about this from what's algebra 1. Less than, do you shade above or below? You shade below. So when you have A, B together, it's going to be linear. A, B as separate statements, it's going to be a quadrant. Absolute value of z, it's going to be circular. And then that's really it for the variety of the sets of complex numbers. There are sets of complex numbers that are way more complicated than this, but that's beyond pre-calc for you guys. Okay, so there's the complex number graphing aspect of it. The last thing we're going to do is talk about how it relates to coordinate. So changing a complex number to its polar form. Now this slide's got kind of just a lot of setup stuff going on. There's some ideas here from the last couple days. But if you think about it, we're not talking about x and y, right? We're talking about a and b. So now a is our cosine, b is our sine, and tangent of theta is b over a. You're going to use the same stuff, the same ideas. And you notice your r, we're going back to r actually, so we're going to use that radius idea. That could be considered to be the absolute value of z, so you got to watch out for symbols. Sometimes it really is like a lot of interchangeable stuff. Here it says r is the modulus. Absolute value of z is the modulus. The word modulus is the distance. There's all kinds of, they all mean the same thing. Theta is the argument, theta is your angle. So if you take the ideas from here and you say r cosine is like my a, and R sine is like my B, then we're going to kind of reorganize a little bit, but what's in red, just by a little bit of quick substitution, is actually what I need to find my complex number in its polar form. So it goes R cosine theta plus I sine theta. The shorthand version of this, which you're going to use for all the problems from here to the end of 8.3, is R CIS. The CIS is C cosine, I imaginary, S sine. Just a shorthand way to write it. It's actually just quicker, easier to work with. So we're going to work on basically changing our complex numbers from A plus BI rectangular to R cosine plus I sine polar. And that's really the last few problems we're going to do. So there's a set of steps. Keep in mind what quadrant you're in. That's going to be important, just like it was doing some of the coordinate conversions. So because when I go do theta, I got to match my theta with the coordinate, the original quadrant of the coordinate I was given. R is going to be the square root of a squared plus b squared. That's x squared plus y squared 2 sections ago, 8.1. Now here we are just doing complex numbers, so our a and b are now our x and our y. Tangent of theta, y over x, 8.1, b over a, 8.3. And then use the final format is how you're going to write it. Okay, so again, it's good to point out what quadrant am I in. A positive, negative coordinate. Positive, negative, I'm in quadrant 4. Purpose of that, again, is making sure that I get the right theta. So tangent theta, b over a. Now remember, this would have come from doing the negative square root of 3 over 2 over a half. Y over x, that's going to be 5 pi over 3. So I know my theta is 5 pi over 3. R, again, a calculation that probably really should be done in your head, that's 2. So what I did there was 1 squared plus square root of 3 squared, 1 plus 3, 4, square root of 4, 2. Do that in my head, Pythagorean theorem in my head. And then when you go to write it, the way it looks in its polar form would be R cosine 5 pi over 3 plus I sine of 5 pi over 3. That's the longhand version. Shorthand goes 2 CIS 5 pi over 3. That's the polar form of a complex number. To be able to do that and use that is actually sort of like the second half of 8.3, and that's where we're going to see the power of complex numbers in their polar form. But for this time, this day, this part of the notes, I mean, it's just getting used to the conversion. How do you change it over? Okay, let's try a few more here before we wrap it up. So again, keep track of your quadrant. Positive, positive is a quadrant 1. So when I go to do my tangent theta, remind yourself you're in quadrant 1. So that's b over a, or 1 root 3, but remember that would have came from this, and that's going to be a pi over 6, so I know my theta in quadrant 1 would be pi over 6. R is square root of 2 root 3 squared plus 2 squared. That's going to be 16, that's going to be 4. So 2 root 3 squared is 2 squared, square root of 3 squared, that's 4 times 3, 12. The other 2 squared, 4, 12 plus 4, 16, square root of 16, 4. So that's longhand version. Shorthand version is 4 CIS pi over 6. After today, I will not use the longhand version again. I'll always do CIS. You guys will too, actually, just to shorten things down. Okay. I'm going to pause the video here for a second because I think I might run out of time. I have to pick up with